Okay, welcome everyone to my continuation of what is algebraic graph theory or what is matroid theory, or whatever. For me, as I said in previous videos, this is kind of the same, which is a very obscure point of view. But anyway, let's ignore that I'm a weirdo and let's just go for it and let's call it algebraic graph theory. Okay, I would continue today my story about matroids. And I have my first main point why I like matroids. So a fair question, if you see matroids, is why? Actually, a fair question, whatever you see, is why anyway. And I'm trying to answer a little bit why I think matroids are cool today. My main reason will follow in a later video, but here's already some good reason. And it comes under a very strange name, and I don't know where the name comes from. If anyone has any idea, let me know. I would be happy if you put it in the comments or shoot me an email or whatever. But it's called a cryptomorphism. Not quite sure what a cryptomorphism is. As I said, not sure. Well, I know what a cryptomorphism is, but I'm not sure where the name comes from. Anyway, so my point of view is here that the first instance answering the question, why is a matroid interesting, is that many definitions coming from many areas of mathematics, combinatorics, geometry, linear algebra, graph theory, and they all end up to be equivalent. And that's very good. That's really very good. And that happens for matroids. And that's one exciting point about matroids. They just come up from various perspectives and in a very equivalent way. Very equivalent is fantastic. Let me try again in an equivalent way. Okay, so let me get going. So, for example, we have seen the basis. And a cryptomorphism is an equivalent but not straightforwardly equivalent way to define a matroid. So sometimes you have an equivalent definition and it's just obvious that the two definitions are equivalent because you just exchange something very basic or so. But for the matroids, it turns out that there's a long list, and I give you some list later, of equivalent definitions. It's not really clear, and it's not difficult, but it's certainly not obvious why they are equivalent. And we have seen one of them. We have already seen one cryptomorphism. I really like that name. By now, I thought the name was stupid, but actually I tend to like it now. I just have to repeat it often enough. So a cryptomorphism, we have seen one of them, namely the equivalence between bases, like here, and linear independent sets, like at the bottom. And first point of matroid theory, at least for me, why are matroids interesting? They're just like a trillion equivalent definitions of a matroid. There are a trillion cryptomorphisms. So let's look at some of them. And the video is way too short. Well, right now I'm recording it, so I could just drag it out forever, but don't worry, I won't. So life is just too short to discuss all of them. So I discuss my favorite ones. And here's one that looks, remember that what I'm going to show you is equivalent to the definitions we have seen. And this one looks just really different in my opinion, and it's the one that comes from graph theory. It's not so obvious from linear algebra, for example, but it will be true by matrix theory if you want. Okay, and it's a notion of a circuit or a circle, how some people call it that can't pronounce the circuit, like me. So I would call it a circle. So you have a graph and you know what a circle is. A circle is something when it kind of circles around, but you remove one edge and it's not a circle anymore. So here, this one is a circle, and whenever you remove an edge, you get a tree. Okay, so this is a dependent set. This is not a tree. So trees were linear independent, remember, where all proper subsets are linear independent, like in my very almost trivial example of a circle upstairs. So in the graph theory example, if you take out an edge of a circle, you get a tree or a spanning tree, right? So that's a circuit. And I really would like to think of them as being obstruction sets for being a basis. So here, all of these are good, all of these are bases, but if you put one more edge, you kind of lose this property. And then you can just backtrack that idea and define a matroid using circuits or circles. And it turns out that the defining properties of a circle are the following. Well, you certainly want some set of them, and it should be non-zero. Okay, forget that one. But then you have this funny clutter axiom, namely, whenever you have a circle and another circle, and one of them is contained in the other, then they must be equal. Essentially, by this, if I take out one edge, it should be linear dependent property. So you never have, they kind of clutter, you never have kind of a chain of them. Okay. And the circuit elimination is what is down below. So if you have two of them that are not equal, and you find a point in the intersection of them, then you can kind of construct another one in a certain way by just kind of removing the point from one and adding the circle to the other. And what is interesting about those three axioms is that they determine what a circle should be, and you can show that by showing that this is equivalent to the other definitions of a matroid. And again, it's not quite obvious, right? So for the bases, essentially what the definition of a matroid did was is kind of it extracted the main properties of a matrix and left us with an abstract point of view. And the same here, it extracts the main properties of a circle, and these are the main properties. And it's kind of not obvious at all, but as soon as you see them, you can easily check it on examples. So that's kind of the whole point here of this part of matroid theory, or matroid theory in general. And this one, and I love this one is fantastic. It's stated as a theorem here, so I copied everything from a wonderful book linked in the description. It's stated as a theorem here, but the theorem essentially says that this definition is equivalent to the other one. But anyway, so we can also write down the abstract defining properties of a rank function. Rank, like in linear algebra now, the rank of a matrix. Okay, and we can just say the rank of something in our ground set of our matroid is just the size of the largest linear dependent subset. Okay. And their sets are linear dependent if and only if they are of full rank. That's exactly what it is. And here's a definition of the rank using matroids. So what are the abstract properties the rank function satisfies? The rank function goes from matrices, if you want, to numbers by producing the rank of the matrix. So what are the abstract properties in this equivalent definition of a matroid? And there's a normalization, fine, that corresponds to the usual kind of thing you see in matroid theory, some non-triviality. More exciting are the other properties. The rank function is increasing, right? So if you have a subset of a given rank and another subset containing it, then the bigger one will be a bigger rank. That's a property you need abstractly for the rank function. Of course, the standard rank function from linear algebra will satisfy that property. And the last one is really fun. So you might have seen that in linear algebra. So in linear algebra, this is usually inequality, but it's in generally only this type of property, and it's called semi-modular. If the rank of the union plus the rank of the intersection is lower or equal to the rank of the sums. And that's, again, a non-obvious property that you just get from this, taking the matroid point of view, because now those three properties, you have a function on your matroid that satisfies this is equivalent to the definition of the matroid itself. And the same as for the circuits. The first one is kind of okay. The second one is something you probably will come up very, very quickly. And the third one is kind of interesting. The third one for the basis was this vector basis exchange, which is not obvious at all why there should be a defining property. Same here for the circle elimination, and here for the same here for the semi-modularity. So if you really think about that carefully, you might come up with this abstract property, but it's certainly not obvious. But using the cryptomorphisms, you kind of cook them up all at once, because they're all kind of isomorphic ways, equivalent ways is the correct word, equivalent ways to define a matroid. And then there are just a trillion more. So we've seen bases, we have seen linear independent sets. I kind of explained, probably failed, circles or circuits. We've seen those. There's a dual notion, which I just skip. Then there's a rank function, and there's a closure operation, which we'll just skip. And then there are the flats and hyperplanes, which I'm trying to illustrate on the next slide. But all of these have interpretations and coming from various different points in linear algebra, graph theory, geometry, combinatorics. So flats and hyperplanes are really more geometry, as the name suggests, and they are all equivalent. And that's kind of absolutely fantastic. So the matroid theory is kind of gathering all of these different fields in one theory, which I think is thumbs up here. Matroid theory, very well done. I love it. So let's have a lot. So this is like linear algebra. This is linear algebra. So whatever. Here's graph theory. This one is probably linear algebra again. You can also, well, everything is combinatorics anyway, so you can also say this one is combinatorics, for example. This one and this one, but anyway. So these guys are certainly, what color don't I have used? Maybe this funny green here. These guys are certainly more geometry type of operation. It's absolutely fantastic. Anyway, these are called cryptomorphisms. There are zillions of them, and I don't even have enough time to talk about all of them. But keep in mind, matroid theory generalizes so many fields and shows so many kind of basic properties of beloved notions. I hope you like bases, for example, and it's just absolutely fabulous. I hope that answers the why a little bit. Here is the notion of a flat, and we'll do flats in the next video because they're fun. But essentially, here's the way how to define them. A quick definition coming from the rank. So the flats are the subset whose rank is increasing with the addition of new elements. Call those guys flats. And they form usually a nice structure, which I will discuss in the next video. But I already have some picture here, so we go through this. But anyway, this is the definition of a flat. If you add something, the rank increases. Well, that's called a flat. And the hyperplanes are like the maximal flats. And you should really think of flats and hyperplanes. So hyperplane is a good name. It's really like you're sitting in space, and now you're taking your vectors, and the hyperplane will be something of almost maximal dimension. Right? Maximal flats that are not the whole matroid, so maximal dimensional subspaces that are not the full space, a hyperplane. That's exactly what it is. And the flats themselves are then smaller dimensional subspaces, like whatever, point, then line, then plane, then 2, 3 plane, whatever the next one is, and so on. And the hyperplanes are then the maximal one, which are not the full space. And they form this beautiful structure called the lattice of a flat, which I'm going to explain in the next video. But this is really the definition directly coming from the rank. And the opposite, how to get from a flat to rank, is just to take the length of the maximal chain of them. Right? So like a line in a plane, in a higher plane, and so on. And just take the length of the maximal chain. Anyway, the only really point here is today there are so many equivalent definitions of a matroid, like fantastically many, and it's really generalizing so many fields. And I hope it really answers the question why. At least it answered the question why for me. Stay tuned. There is even a better reason to study matroids, so an even better one. But we'll go there later along the way, not along the way, in later videos. Anyway, I hope you enjoyed this video, and I also hope to see you next time.